So yesterday we took a look at this idea of formal methods for security, and in particular why programming languages are a fantastic fit for that. And we did a brief case study on non-interference, which we'll be digging into much more today and tomorrow. And then we got through some concepts, some key security concepts, including information security. We didn't get up to things like trust in the threat model, but we'll be covering those as we need it today and later on. Today, though, what we're going to be focusing on is starting to look at semantic definitions of non-interference and other information flow-based security guarantees. Just before I jump into that, though, let's go over again what the motivation is for non-interference-like guarantees. So the key idea is that we have some computer systems that handle not just sensitive information, but a variety of sensitive information. Say information from different web app users or information of different medical patients. So how do we ensure that the system is handling that information appropriately, securely? Now, access control is typically not enough. And by that I mean access control is able to control who can access the information, but typically doesn't control what happens after that information is accessed. And if by handling information securely, we mean that certain entities don't learn secret information, for example, then access control isn't quite right. It's getting close, but it doesn't actually directly achieve our notion of security. So that motivates the idea of information flow security guarantees. So information flow guarantees are extensional guarantees about security. Now, by extensional, I mean that we define security in terms of the observable behavior of the system. Right? By contrast, an intentional guarantee is one that might define security in terms of the internal operation of the machine, how the computer system achieves the computation, the intention of the system. So in terms of extensional guarantees, this might be about what outputs the system produces. By contrast, an intentional guarantee might say something like, before you pass a string to the database, you must make sure that it's escaped any special characters. Right? That's about how you're implementing it. It's about details of the code patterns or the way that you're putting together the computation that comprises the system. So with respect to the semantic guarantees that I'll be talking about today, they're all going to be extensional, about the behavior of the system. Tomorrow I'm going to talk a bit about the enforcement of these guarantees. And when we talk about the enforcement, yes, we will be talking about the intention of the system, the implementation details. But we're going to put that off until tomorrow. Okay. So this idea of non-interference has been around for a while. Maybe Cohen back in '76 introduced the key idea of strong dependency, which is really the foundation of non-interference as it's used today. And the intuition that Cohen uses is to define information flowing from one entity, entity A, to another entity B, when B depends on or is influenced by A. So think about that as being the low security output might be influenced by the low security input. Okay, that's a flow or a dependency. Now, given a deterministic system H, with inputs including A and output including B, B strongly depends on A if there are two executions of the system where the inputs are exactly the same except for the entity A. And in those two executions, the output, entity B, differs. Right? So the intuition here is a strong dependency. The output B has changed when the only thing that varied was the input A. Okay, so that's the notion of strong dependency. And we're going to define security as the absence of some of these strong dependencies. In particular, an absence of a strong dependence from secret inputs to public outputs. Okay, so we actually saw an instantiation of this yesterday with our definition of non-interference in the setting of IMP with two security levels, high and low, a context that maps variables to high and low. Based on this definition of low equivalence, two stores being low equivalent when they are equal on all of the low security variables, we were able to define non-interference. So that is, for all stores sigma 1, sigma 2, sigma 1 prime, sigma 2 prime, if sigma 1 and sigma 2 are low equivalent, this is the input to the system, and we have two executions of the program C, terminating with sigma 1 prime and sigma 2 prime respectively, then the low outputs are equivalent. Sigma 1 prime is low equivalent to sigma 2 prime. Okay. So this was the same definition that we saw yesterday. And the intuition here is that we're saying that there are no strong dependencies from high inputs to low outputs. So that is, these two executions are exactly the same, except that they might differ on the high inputs. In particular, they are equivalent, they are equal on the low inputs. And the outputs, the low outputs are equivalent, right? That is, there is no strong dependency from high input to low output. Yeah, question? You're asking if the definition is vacuous. No, it isn't, because sigma 1 and sigma 2 are equivalent on low inputs, but might differ on high inputs. And this is a universal quantification for all sigma 1 and sigma 2. So what we're actually looking at here is for all possible pairs that are equal on low inputs, but differ arbitrarily on the high inputs. So what this is saying is that there's no possible high inputs you could provide that cause a difference in the low outputs. That is, there is no strong dependence, no flow of information from the high input to the low output. Does that help? Great, thanks for the clarification. Any questions about this definition of non-interference? We're going to be looking at a whole lot of variations of this, so making sure we're comfortable with this one is going to be useful. Great. Okay, so here's that diagram from yesterday, talking about the real system, modeling the system, reasoning about the model. Now, we critiqued very quickly this definition of non-interference as a model for reasoning about security of real systems. There were a few issues that we had with it. One was that IMP is, not a great model for computer systems. We also talked about the idea that, there are things going on with the execution of the system that we think are reasonable to observe, such as whether or not the program execution terminates. So in general, when we're trying to formulate an information security guarantee, we have to make some design decisions in our model. Right? We need to choose which entities are under consideration. So that is what we regard as being inputs to the system, what we regard as being outputs to the system, what we regard as being appropriate handling of information. Right? And that non-interference definition was very simply no flows from secret inputs to public outputs. But as we'll see later on, that is overly restrictive, perhaps. So a lot of the research on information flow over the last 5 or so decades has really been tweaking these definitions in various ways. Looking at different threat models, so that is thinking about what the adversary might be able to do, might be able to observe about the system. Thinking about the computational model, going beyond simple imperative input and output programs to things that are more realistic, that more closely reflect the actual computer systems we care about. And also thinking about refining that notion of what is appropriate information flow. That is, what are the conditions under which information is allowed to flow between entities. So what we're going to be doing this lecture is really looking at some of these issues. looking at the computational model, that is the entities that are involved in the execution of a system. Looking at the threat model, that is the entities which the adversary is able to interact with, able to observe or manipulate. And then thinking about specifying which flows are going to be allowed or forbidden between the entities. Okay, so this is the plan for today. And to give you a bit of a roadmap for it, as I said, we're talking about the threat model, the computational model. We'll talk about reclassification, so more detailed, more fine-grained ways of specifying the flows that are and aren't allowed. But before I jump into that, I'm actually going to talk about labels and flow relations as a way of helping us provide useful specifications of non-interference and similar guarantees. Okay, so by a label, what I mean is a syntactic object that we're going to associate with some of the system entities. So we've already seen things like high and low or secret and public as labels, but there's actually a whole range of possible labels that we might want to choose in our modeling of a system. Trusted, untrusted, we might want to use specific principles that are interacting with the system, say the web application users, Alice, Bob, Charlie, and so on. We talked about multi-level security, a military classification system where you have a level, public, confidential, secret, top secret, combined with a compartment, one or more compartments, nuclear, cryptography, biological, and so on. So the idea of these labels is that they allow us to kind of succinctly group entities together in a way that we can use these labels to specify permitted or forbidden flows between entities based on the labels. So for example, we might say that entities labeled public, the information associated with those entities is allowed to flow to entities associated with secret. Okay, so this is using the labels to succinctly describe permitted or disallowed flows between entities. Now these labels might have a rich structure. We'll talk about structure in just a moment. But I want to emphasize that the labels themselves are not the policies. The labels are just this way of us grouping together entities or just modeling important things within the application. But then we're going to be using these labels to describe which information flows are allowed and not allowed. And we do that by using what are called flow relations. That is, we can express an information flow policy as a flow relation, this ordering, which I'll refer to as less than or equal, on a set lambda, capital lambda, of labels. And intuitively, if I have two labels, L1 and L2, if L1 is less than or equal to L2, then information is allowed to flow from L1 to L2. That is, if I have an entity associated with the label L1, information from that entity can flow to an entity labeled with L2. Okay, so what structure should this flow relation have? Yeah.
Reflexive and transitive.
Reflexive and transitive. Great. Why is that?
Reflexive because you should be able to flow to things with the same label, and transitive because if you give access to some entity label X and that gives to Y, then you kind of have that transitive flow anyway. So.
Right. So those are great reasons. We want it to be reflexive so that an entity can information can flow to itself. Right? Otherwise, it wouldn't make sense if I'm not allowed to learn information associated with me. Might be challenging to have a computer system that does that. Transitivity is good as well. It kind of, in many ways, enables compositionality, right? That we're able to compose systems together. Let's say a component that information flows from L1 to L2, compose it with a system that flows from L2 to L3, and if both of those systems are individually secure, that is, those flows are permitted, when we combine them together, we still have permitted information flows. So that'd be nice to have if our flow relation is transitive as well. It's going to make our lives easier when we think about these systems and the security for it. Now, if we have a partial order that's both reflexive and transitive, this is known as a preorder. We might also want to add what's known as anti-symmetry, in which case we'd have a partial order. Sorry, I misspoke. If we have a relation that's reflexive and transitive, it's a preorder. So Dorothy Denning actually argues that we should use, for this flow relation, a join semilattice. So let me explain what a join semilattice is, and then we'll talk about why. So a join semilattice has a least upper bound operation. The least upper bound operation is written with this square cup. And as the name suggests, least upper bound operation, it is both an upper bound and a least upper bound. So by upper bound, I mean if we have two labels L1 and L2, the join of L1 and L2 is an upper bound of L1. That is, L1 is less than or equal to L1 join L2. And it's also an upper bound of L2. L2 is less than or equal to L1 join L2. It is the least such upper bound. And by that I mean if we have any other label L3, which is an upper bound for L1 and L2. So here we have L3 as an upper bound of L1 and L2. Or then L1 join L2 is less than or equal to L3. Right? L1 join L2 is the unique least upper bound. So why is a join semilattice structure a good one? Why do we think it might be a useful structure in our flow relations? Sorry. Let's see. So let me phrase this in a wrong way. We definitely want some sort of upper bounding operation, so that if we have information that, let's say, on a if then else branch, where a variable is assigned on both branches, what should be the label of that variable after the branch? Should definitely be an upper bound of the information on each of the branches. So that'd be nice. Upper bound operations will give us a way to put a label on variables that can sort of describe different paths through the program. So that's great. We can also use upper bound operations even without if then else statements. Suppose we just have a binary operation. So data A and B labeled LA and LB respectively, and we combine them. This O plus operation, maybe it's addition, multiplication, whatever binary operation you want. So what should be the label of A O plus B? Right? So it should definitely be an upper bound, right? Because the result of A O plus B might reveal information about A, and it might reveal information about B. Right? So the level of the result should be at least as restrictive or allowed to flow to, can flow from LA and from LB. We really want it to be a least upper bound so that the following kind of pattern can work. So suppose that we had two upper bounds, LD1 and LD2, and we compute C is equal to A, O plus B, and then assign C into both D1 and D2. Okay, so D1, the label of D1 and the label of D2 are both upper bounds of LA and LB. So it should be okay for us to assign C into the variable D1 and assign C into the variable D2. Flow is allowed from LA to LD1. Flow is allowed from LB to LD1. And same with LD2. So what label should we have for C? C, the label of C needs to be an upper bound. If it's anything other than the least upper bound, then we might end up rejecting this simple program. Right. So in some ways, having least upper bounds is, again, something that's going to help us with compositionality. Right? Being able to be precise as we can be in our labeling of, let's say, intermediate results as we're thinking about how information flows through a system. Any questions about joint semilattices? This is a very hand-wavy motivation for what's going on. Yeah.
I have a question, not about joint semi-lattices, but about transitivity.
Okay.
Has there been work that looks at sort of non-transitive relations? Because I can imagine that coming up.
Yeah. Has there been work that looks at non-transitive relations? Yes, there has been. If I have time near the end of the class, I have a slide on it. But to be honest, I was going to cut that if we were out of time. So we'll see if we get to it. Thanks for the question. Okay. So we have this notion of labels, right? These syntactic objects that can kind of, that we're going to be using in these flow relations. Let's use these labels to give a more generalized definition of non-interference. Okay, so let's suppose that we have a lattice lambda with a flow relation on it. These might be things like confidential and public. Maybe there's some joint semi-lattice over principals. Maybe Devin is Alice and Bob's manager, and so is allowed to see anything Alice and Bob can see, with some distinguished elements, the bottom of the lattice, that is the most public thing, and the top of the lattice. By the way, in most of today, I'll be focusing on confidentiality, by the way. Here is the multi-level, an example multi-level security lattice, where essentially the labels are pairs of a classification and a set of compartments with ranging from secret to top secret and two compartments, nuclear and crypto. Here is a power set of principles. Maybe this is the set of principles that are allowed to read or learn about information. So at the bottom of the lattice is the most public thing. All of the principles, Alice, Bob, and Chuck, are able to learn the information. At the top of the lattice is the empty set. None of the principles can learn the information. Yeah. Okay. So let's suppose that we have this, some set of security levels, the flow relation on them. Like before, we have a context mapping variables to, in this case, security levels, labels. We're going to generalize our notion of low equivalence to L equivalence, where we say that two stores, sigma 1 and sigma 2, are L equivalent if they're equal on all variables that are less than or equal to L. So that is, if variable x, if its label can flow to L, then sigma 1 and sigma 2 agree on the value of x. Okay. Now we can present a slightly more general definition of non-interference. Right? So for two stores, sigma 1 and sigma 2, if they are L equivalent, and we have two executions resulting in sigma 1 prime and sigma 2 prime respectively, then those outputs, sigma 1 prime, sigma 2 prime, are also L equivalent. And so I'm highlighting in blue here where this definition differs from our previous definition of non-interference. So really all that's going on is this, instead of, if you will, hard coding a specific security joint semi-lattice of high and low, we're now allowing an arbitrary set of security levels. Any questions about labels, about this slightly more general definition? Yeah.
I think this question was asked yesterday, but I'm sorry if I'm repeating it, but in this case, since we're using big step semantics, could there still be a case where a subpart of the program violates non-interference, but then you update the store to sort of mask that?
Ooh, are we concerned about a case where a subpart of the program violates non-interference? That's a great question. What's interesting here with this definition of non-interference is that it's an extensional definition. All we really care about is what command C does, how it takes the inputs and produces the outputs. Now, when we talk about violating non-interference in between, that is, maybe it takes some high input, temporarily stores it in a low security variable, does something with it, but ultimately the output satisfies this condition. Maybe it zeroes out all the low security variables before it terminates. Well, then this would satisfy the definition of non-interference. What we're going to see tomorrow, though, is when we look at how to enforce non-interference, the way to enforce it is to actually look at the details of the command C. And as we enforce it, we're actually going to likely enforce a stronger guarantee. Something like, at every step of the way, we're maintaining something stronger than we need, but that stronger thing will imply non-interference. This is the same kind of thing you see with, let's say, even a type system for type safety, for making sure that a program doesn't get stuck, right? You could actually write lots of programs that are not well typed, but do not get stuck. But the type system is conservative and rules it out. And in general, that's what happens with a lot of program analyses and enforcement mechanisms, is that it conservatively enforces the thing that we actually care about. So yes, when we look at enforcement, we're going to be ruling out programs that violate our invariant midway through in order to make sure that it enforces non-interference. But this definition of non-interference actually says nothing about how C operates and what it does. All it cares about is the observable behavior of the system, which in this case is the initial store and the final store. Does that help clarify? Cool. Thanks for the question. Yes?
Sorry, the definition of the L equality, just to
Yeah.
clarify, so if you have an X that in sigma 1 it flows to L, but in sigma 2 it doesn't, then this would not work, right? Then this equality would not be, or is that not?
So the flows relation is over the labels, over the set of security levels. The flow relation, capital lambda, and this inequality relation, they're independent of the program C, they're independent of an execution of C, and so on. And so you're right, the flow relation is fixed. That's another...
X maps to 1 that goes, then if they map differently, one is above L and one is below L?
Yes. So I'll also note that the context gamma, the thing that maps program variables to labels, that's also the same for both executions. And so we don't actually get into that problem that you're talking about what if the flow relation or the mapping of variables is different in the two executions. Now this is again a modeling issue, right? This is taking us towards a more expressive notion of non-interference, where we could have a rich set of labels that describe things that we care about with respect to security. But we're maybe not yet capturing things like, you know what, in real programs, they're more expressive than them. They can dynamically allocate memory. And how do we think about the security levels of newly allocated memory during execution? What if those two executions allocate different memory locations? How do we talk about equivalence of memories after that? So those are good questions. We'll touch on not exactly that one, but the idea of extending the computational model and extending the attacker's observations to be more realistic. And what ends up happening, to long story short, the definition gets more complicated, right? Even though the same fundamental ideas are there. Does that help? Okay, thank you. Yeah.
So this definition seems stricter than the definition before because L here is universally quantified, which seems like every label is a low label.
Yes, well noticed. The security level L here, is universally quantified. So what we're requiring for non-interference is that no matter which security level you choose, you're not interfering with respect to that level. Right? I could have given a definition that was non-interfering at level L if we wanted, but we're actually going to be requiring that for any security level we're non-interfering. And so, right, the idea of what is low security and what is high security is kind of relative to where in the lattice, where in this label lattice you're looking. Yeah.
So just for these labels, like the structure of them, you said that there can be different entities and we can give them different permission levels or whatever. I'm curious, does the structure of these labels, do they follow propositional logic?
There are a lot of different label systems that you can have. Some of them are based on propositional logic, where you might use a join semilattice where the ordering is essentially based on logical implication, and higher up in the lattice is conjunction. Lower down in the lattice is essentially like disjunction. So there's actually this idea that you can have a really rich label structure, which can help with the expressiveness of the security guarantee that you're pinning down. But there are other ones that, we saw an example of a power set lattice, right, where the ordering of the labels is based on set ordering. Okay. So this is taking us towards more expressive notions of non-interference, generalizing the labels. Let's think about more realistic threat models. So by the threat model, I mean how the adversary interacts with the system. Now, a stronger threat model means that the adversary has more ways of interacting with the system. And that is, the more ways that they have of interacting with the system, the more opportunities there are for information to flow to and from the adversary. So Lampson categorized the idea of information channels. Information channels convey information. And Butler-Lampson categorized them as legitimate channels and covert channels. Legitimate channels are information channels that are in fact intended to convey information. So these would be things like input-output on the console, network messages, files, reading and writing files, and so on. By contrast, covert channels are aspects of the system that are not intended to convey information, but nonetheless do. So this might be things like how long a program takes to execute is going to be conveying information maybe about the data the program is manipulating. How hot the CPU gets, acoustic emanations from imperfections in the chip manufacturing can actually reveal information about what computations the chip is doing. Whether or not you run out of memory, right? Memory resource exhaustion is a covert channel that might convey information about the computation that's happening, even though it's not intended to. Covert channels are further subdivided, and a set of side channels are the covert channels that can be exploited by a passive adversary. So that is an adversary who's simply observing the system, as opposed to actively interacting or manipulating it. So a side channel reveals information to a passive adversary. And that includes things like the execution time of the system and so on. Okay, so with this idea of information channels, legitimate and covert channels, let's think about our definition of non-interference. Now, we already talked about the idea that we might reasonably expect an attack to observe whether or not a program terminates or diverges. Our previous definition of non-interference is what's known as termination insensitive. If we look at that definition, essentially what's going on is that here in our precondition, we were restricting our executions only to the terminating executions, right? That is, we require that C1 sigma 1 executes and terminates producing sigma 1 prime. Similarly with sigma 2 and sigma 2 prime. So what that means is that the program, while I is greater than 0 do skip, does actually satisfy non-interference. Mainly because any two executions where it terminates, the low outputs are the same, right? But if an adversary was able to observe termination versus non-termination, they will clearly learn information about that high input. So of course, we can modify our definition of non-interference to account for this side channel, for this termination channel. The key idea is that we want to make sure that the termination behavior of our system is determined by the low inputs. That is, given two initial stores, sigma 1, sigma 2, that are low equivalent, L equivalent, either they both terminate or they both diverge. Okay, so here's a definition of termination insensitive non-interference. So if sigma 1 and sigma 2 are L equivalent, then either both of those executions terminate and the resulting final stores are L equivalent, or both executions diverge. Okay, any questions about this definition of termination-sensitive non-interference? Yeah.
Maybe you gave us only one, but how much of it again is to the value? Like it seems like just whether a program terminates not isn't much.
Right, whether or not a program terminates is a pretty coarse-grained side channel, if you will. You kind of get one bit of information, if you will, for every execution, did it terminate or not. And so you're right, we might be interested in a more realistic approach of timing sensitivity. Can an adversary observe how long the execution takes? You can actually think about termination sensitivity as an extreme form of timing sensitivity, where the attacker can distinguish between finite and infinite. Okay? But more realistically, we might have attackers with stopwatches and who are able to get finer-grained notions of how long an execution takes, even if it does terminate. There's actually a few ways that we can think about timing. One is that, if we have a computational model of our system, maybe this is expressed as a small step operational semantics, right? That we are expressing the computation in terms of discrete steps from one configuration to another. So we might end up describing the timing, the amount of time that a computation takes, as simply the number of steps that it takes in this model, right? So that's nice and simple. It fits with the way we're modeling computation in a clean way, but there's a really big gap between that and reality, like a real system that's executing on an actual machine with a complex microarchitectural implementation. How long that actually takes to execute is pretty far divorced from our very clean, small step operational semantics of a system. So we could imagine instead, if you will, the wall clock time, the external timing of a system. Could perhaps be closer to reality, but to be honest with you, it's really hard to model accurately. It's hard to capture in a model all of the things that it depends on, the memory hierarchy. So that is the many different layers of cache and how the cache operates, how different variables and memory locations are split into different cache lines, how the CPU might do its pipelining, how it might do speculative execution and branch prediction and so on. There's also another notion of timing we might be interested in, internal timing. And think about this as if you have a system that has multiple threads or multiple processes running, even if that thread an adversarial thread, if you will, doesn't have access to wall clock time, it might still be able to observe the order that events happen in. So that is, if there's a race condition in your concurrent program, the order in which that race is resolved might reveal information about how long relatively computations are taking. So when we think about these different ways of timing, we can actually think about modeling them. Well, for these first two, you could conceptually think about modeling this just by, let's say, having some additional state, a timing variable that somehow increases as execution goes on. Right? For the simple number of steps it takes, it just increments every step. Maybe we have, as realistic a model as we can make for wall clock time, where it increases during execution based on whatever our model says. Maybe this is trying to approximate the actual number of seconds time elapsed. Maybe it's doing something like counting the number of register accesses and main memory accesses, or more accurate models of cache, so on and so forth. For internal timing, this is really about concurrency. And so in a few slides, we'll actually talk about concurrency and some ways that we might have to think about it. So I'm not showing you here an actual definition of non-interference. I'm just waving my hands and talking about how we might imagine coming up with a more sophisticated model that's trying to capture these notions of time in various ways. Okay. Question?
Just maybe a quick clarification on the last one. Are you saying that the thread is, in the thread model, is an adversary? Are you saying that the internal timing, the internal scheduling can reveal information in another more legitimate channel?
Great question. When in this last one, internal timing, how are we thinking about the thread? I think there's at least a couple of ways to think about it. One is simply that the relative order of events might reveal information, right? And that information might flow through a system. So for example, a thread that reads a value of a variable x, where there's a write-write data race on it, might learn information about the relative order of those writes. And that information might flow through the system, and we're going to be concerned about tracking and restricting that when it comes to enforcement, but even extensionally, the fact that that thread reading the variable might have a strong dependency on information might be important for us to know about. In some settings, we might actually be thinking about the thread might be, quote, controlled by an adversary. Maybe the adversary is able to contribute code to the system, and they provide code for a thread that is actively trying to detect who won a race and thus learn information. So we're not quite there yet in terms of our adversary model, but just the idea that this internal timing channel is an information channel. Information can flow by it might mean that we want to make sure that our security guarantee is accounting for that information flow in the same way that we might want to account for wall clock time in our definition of security. Does that help? Okay, thanks. Yeah.
If you add this new variable to the state, this time variable, could you add like another, like a sleep primitive or a sleep until upper bound primitive that like sleeps until upper bound that, and if you do add this primitive, what does the information flow of this primitive look like?
Right. So I think what you're pushing towards is how could we mitigate this timing channel?
Yeah.
Maybe by having threads sleep, maybe by having them sleep random amounts of time, or make sure that this computation always takes a fixed and predictable length of time, maybe by idling after it's finished the computation if needed. So that's great that you're thinking ahead to the enforcement mechanisms. The thing that I want to emphasize for the moment is that we want to define our notion of security first, so that then we can think about ways that we can enforce it. And those might be ways that you could mitigate a timing channel, albeit inefficiently, right? By, we throw away all the performance benefits we get by really smart microarchitecture by making sure it takes a fixed amount of time. But I think one of the important things is to first realize that this might be an information channel and to be able to capture in our model or in our security definition that it might reveal sensitive information is the first step. Yeah?
For termination-sensitive non-interference, how would an adversary recognize that a program isn't terminating versus just taking a long time?
You can't really determine between has diverged versus taking a really long time. But depending on what the computation is, you might have a reasonable guess. If you have a program that's meant to be doing a binary search of an array with 10 elements in it, and it's taken you 5 minutes, you probably have a bug in your code and it's not going to terminate. So those kinds of things. But yes, we can't really tell. Yes, question at the back.
Are we meant to be thinking about time separately, like separate the time that it takes to do computations on low security material versus time it takes to do computations on high security materials?
In our security, you're asking in our security definition, we're separating on time spent on low computation versus time spent on high computation. Yeah. What I'd say is no, not directly. We might, when it comes to enforcement and we think about the implementation of a system, that might be one of the ways we are trying to enforce controlling that timing channel. But in terms of our security definition, we're kind of just talking about the amount of time. Now, an adversary, I'll talk about later, we typically assume the adversary knows the code or knows the computation that's meant to be happening. And so combining that knowledge with how long the total time takes, they might be able to infer information about secret information. But the definition of security is not making any notion about time spent on high computation, time spent on low computation. It's really more just describing how the adversary is interacting with the system. If they're able to observe how long an execution takes, it might be good if our model captures to some degree of precision how long a computation takes. So this is, the thing I really want to emphasize here is the process we're going through today is thinking about how we make that model better, how we more accurately express what we think an adversary might be doing, how we more accurately express what the real computational system is doing in our computational model. Okay. So one of those areas that we want to be more precise on perhaps is interaction. We've so far been looking at this batch-like model. System gets all the input, does all the computation, and produces an output. But of course, most systems are interactive, right? And an adversary makes observations during the execution, and inputs are provided throughout execution. So we can extend our imp program to try and capture this. Let's suppose that we add input and output commands. So take an input from a channel associated with label L, put the result into X, output a variable X to a channel L. We modify our semantics. I'm going to assume that we have essentially a small step semantics where if I take one or more steps from this configuration to that configuration, it might produce a trace tau, where a trace is either empty or a trace with an input event at the end or a trace with an output event at the end. Right? So a trace is kind of capturing the history of the inputs and outputs of an execution. So then we can use this computational model extension, traces, to define a notion of non-interference that takes interaction into account. Intuitively, if we have initial memories that are low equivalent and two executions where the low inputs that are provided are the same, then the traces should be low equivalent. That is, the low inputs and low outputs should look the same. So to phrase that more formally, if we have two executions from low equivalent, L equivalent stores that produce traces tau1 and tau2, and the inputs in those traces are L equivalent, then the traces tau1 and tau2 are L equivalent. That is, the inputs and outputs and the interleaving of those at level L and below are identical. So I'm not giving you the exact definitions of these equivalence relations, but hopefully they're intuitive. Any questions about this? Yes?
The number of traces you have is like exponential, right?
It's going to depend on the program C.
I guess what I'm trying to get at is like, can you like efficiently do things with these?
Can you efficiently do things with traces?
Yeah.
Depends on the thing that you're trying to do. At the moment, what we're doing is defining security. So this is a definition of what we mean by security. The question of, is it decidable whether or not a program satisfies this definition? Or do we have efficient mechanisms to conservatively decide whether or not a program is secure? We haven't gotten to yet. But yeah, this is a more complex computational model. IMP was Turing complete without this extension. This is now increasing the expressiveness of it. But it was, you could always encode this in the non-interactive version of IMP that we had. Okay. So once we have interaction, we actually have a richer notion of termination sensitivity, if you will. So beyond, now instead of just figuring out whether or not a computation terminates or doesn't terminate, we could actually distinguish whether or not it's going to produce another output or another event, if you will. So there is actually a notion of analogous to termination sensitivity known as progress sensitivity. Has the computation diverged, or is it going to make progress? I'm not going to put the definition up there. Again, as we have more realistic and more interesting threat models, we end up with more complex definitions. And so I'm not going to take the time to put all the background up there, but the intuition is that it generalizes termination sensitivity to progress sensitivity. Yeah?
But maybe just one quick question without the definition. So progress sensitivity here would be defined over our traces, not about our whatever small step semantics. So we're only like one step would correspond to one element on our trace.
Yes, our idea of progress sensitivity is whether or not the trace is going to have another element added to it, not about how many steps the computation is taking. We talked about the idea of the attacker knowing the code of the system. And so this is another aspect of the threat model. Are we assuming the adversary knows the code? Can they modify or provide parts of the code to the system? Again, these are ways of describing how the adversary is interacting with the system and our assumptions. With non-interference, we normally assume that the attacker does in fact know the code of the system. And that's sort of implicit here in this definition, that with the idea being that if a program C violates non-interference, if we have some low security variables that differ in the outputs, we're assuming that that is bad, that that is going to allow the attacker to infer infer some information about the secret inputs, the high inputs. And that is really assuming that they know what the command C is. If they had absolutely no idea what the command C is, then that relation between inputs and outputs is almost arbitrary. Right? So implicit in this definition of non-interference is that the attacker knows the program C. There are definitions of non-interference that allow the attacker to provide some code into the system. This is known as an active adversary. You can actually model this or simulate it if the attacker is able to provide any input to the system at all, right? You could imagine that one of the inputs is the text of a program, and the program includes an interpreter. Or if you're in the lambda calculus, you can imagine that one of the inputs is in fact a closed lambda term, right? And so the input data is in fact computation. So to be honest with you, the idea of the attacker being able to provide code isn't actually a huge leap in the model, although even though it might seem to be a significant change. As Ali was talking about in her talk, in her lecture today and yesterday, one of the things we're concerned about is the computational ability of the adversary. That is, what is it that the attacker can compute? And so, for example, if we had a program that's performing encryption, and I'm going to wave my hands and pretend that we have somehow or other have an interesting deterministic encryption system, we might ask whether this program is secure. In this program, we have two messages, a low message and a high message, and a secret key that we use for encryption. We encrypt message 1 with the key and output that to low. So we're going to assume that the low observer, the attacker, knows both message 1 and the encryption of message 1 under the key. We then output the encryption of message 2 in the key. So from this information, essentially kind of similar to a chosen plaintext attack, does the attacker know what message 2 is, the secret message, or can they figure out what the key is? And in some ways, with an unlimited amount of computational ability, the attacker could figure that out. That's kind of why in the security games that Ali was presenting, we're interested in limiting the power of the adversary, say to some certain number of steps or having negligible probability, so on and so forth. So some versions of non-interference, particularly those that are wanting to reason about the computational model of cryptography, will end up assuming some computational limits on the attacker. Right? Again, I'm not going to go into an actual definition of this, but some of these definitions end up touching on the definitions that Ali was presenting about security-like games and about not being able to distinguish things with more than negligible probability. More generally, we've been going through and talking about what an attacker can observe about a system. We can actually just generally describe a view of a system, a function from the system, state, or maybe the history of the execution to an attacker's observations. So that is the idea, is that an attacker sees some subset of the execution trace, the execution's history. This might be appropriate, say, for a distributed system where there are many physical machines, some of which might be compromised or owned by an attacker, who gets to observe all of the computation happening on those nodes of the distributed computation. Maybe with an embedded device, it's reasonable for the attacker to observe the power consumption of the device, maybe with an amp meter or something on the power supply. So we can come up with a definition of non-interference that really just generalizes this idea, assuming that we have some, I don't know, some history of the computation, some generalized notion of trace to maybe the sequence of states that's produced, and some function that tells how an attacker at level L what they're able to view about that history of the computation. Right, so this is a generalized notion of non-interference that is essentially just capturing the idea of you've got some model of execution producing a history tau, you've got some function that says what the attacker can observe on it, and if we have L equivalent inputs, then what an L attacker observes should be the same. So we've touched on a whole lot of different attacker abilities, different threat models. Here's a summary of some of what we talked about, as well as a few more things that we didn't touch on. And there's a reference in the slides if you're interested in looking at more of that. I also want to talk about extending our computational model in various ways so that we have more realistic systems. Sorry, question at the back first.
I'm just curious about the threat model. Are we able to use these techniques to view humans as an extension of the model? So to mitigate leakage from sources.
I'm sorry, I don't quite understand the question. Are we able to use views as a...
Are we able to view the human interacting with the system as an extension to the model itself, rather than having to make a separation between the model?
That's a great question. When we have entities involved in the system that are, for example, humans, or even other computer systems, where do we draw the boundaries of our model? So this actually comes down to a question of what is a good model. And it really depends on what our goal is. There are definitely some models of non-interference where it's not quite modeling the human, but included in the model of the system is the thing that is providing inputs has a strategy. That is, the thing that is providing inputs is a function from the observed history of the trace so far to the next input value. Right? So is that modeling the human? Kind of. It's sort of modeling some entity that is observing things and then deciding what the next input to provide is. Would you want to include a model where you have humans and psychological models of humans in there? Maybe. It depends about what you're trying to prove and whether or not the model is a good thing for reasoning about it or not. But the same thing applies to external computer systems as well. If I have a distributed system, where am I drawing the boundary of what I care about? Do I want to model every single computer on the internet? Probably not. Do I want to model a subset of them and assume that they have connections to external things that I'm not modeling? Maybe. Okay. Computational model is abstracting the system functionality. It's very tightly coupled with a threat model. We already saw that when we talked about the attacker being able to interactively observe system execution. We actually needed to extend our computational model with input and output. But there are other aspects to the computational model that we haven't explored yet. One is non-determinism. So far, we've only looked at deterministic systems. And interestingly, the definitions of non-interference that we've given so far don't hold for non-deterministic systems. So let's consider the following program. Suppose we have a non-deterministic choice operator, this narrow bar. A1 choose A2, non-deterministically chooses between A1 and A2. So this program, low is assigned 42 or 7. Strangely, this doesn't satisfy non-interference. I say strange because this program does not directly manipulate any secret information at all. Right? The program doesn't even mention any program variables with secret information. Why might this fail to satisfy non-interference? Exactly. So if we actually look at the definition of non-interference, it may not satisfy it because low equivalent memories might end up with different low states, one where it equals 42, one where it equals 7. Now this might be a security concern because we don't actually know how this non-determinism is being resolved. Maybe it's actually going to be resolved based on some secret information. Now this is what's known as a refinement attack. The set of possible behaviors of the system might be refined down to a subset of those, perhaps revealing secret information. So there are some notions of non-interference that do work in non-deterministic settings. One is known as generalized non-interference. And the key idea here is that the secret inputs do not constrain the set of possible public outputs. That is, any low observable behavior is compatible with any secret input. And the definition of generalized non-interference is a little more complicated. What it's saying is that if I have two executions from sigma 1 and sigma 2, where sigma 1 and sigma 2 are low equivalent, then I can actually come up with a third execution, a store sigma 3, which is low equivalent to sigma 1, and has all of the secret inputs from sigma 2. And when I execute from sigma 3, I get something that looks the same as sigma 1. So what this is saying is that any high input that I took from execution sigma 2 is compatible with the low inputs from sigma 1, and the output looks exactly the same as sigma 1. The low outputs are the same. Okay. So that is essentially any possible secret input is compatible with any low observable trace, any low observations. So this is maybe a good notion of security. Kind of determining whether or not it's a good notion is somewhat beyond what we can do with formal methods. Part of the challenge here is that it requires a system to actually exhibit all possible behaviors that we could have. The thing is, though, it's often useful for us when we really actually implement a system to refine the behavior of the system. Right? This is kind of when you implement a module, you might be having more restricted behavior than would be that might be shown by the module's interface. So a notion of observational determinism that actually Steve Zdanswyk and Andrew Myers rediscovered and expanded on in the context of non-interference requires that the resolution of low non-determinism doesn't depend on secret information. So for example, if we have a concurrent system where we have a scheduler and that scheduler is scheduling threads, right? The scheduler choices are one of the ways that non-determinism is refined. The order that threads are scheduled is up to the scheduler implementation. So observational non-determinism would mean that the behavior of the scheduler, which threads it's choosing, has to be independent of secret information. So what this means is that you might have to make sure that the scheduler doesn't choose things based on how much computation they've had so far, because that might depend on secret information, or how much computation is estimated to remain. Something like a round-robin scheduler that always schedules threads in a fixed order might be okay. Interestingly, it turns out that observational determinism essentially has the same definition as non-interference, the idea that the low view is determined by the low inputs. Okay. So this is nice in the sense that it isn't subject to refinement attacks. But on the downside, we actually sometimes like to have non-determinism in our system. Right? It's sometimes good for us to be able to have non-deterministic programs. Related to that idea of non-determinism is the idea of probabilistic programs. Fun things, very powerful, very useful. Stephen H. is talking with you about. So far, we've seen possibilistic definitions of non-determinism. And intuitively, these may not capture some of the information flows we care about. So for example, if we look at this program that picks A is non-deterministically chosen to be a number from 0 to 999 inclusive. If we happen to choose 0, then we non-deterministically choose either 0 or 1. But otherwise, we actually reveal one bit of secret information. So if this would satisfy some kind of possibilistic non-determinism thing. All low behaviors are possible regardless of the secret information. But if we're actually choosing this number A, let's say according to a uniform distribution over the numbers 0 to 999, chances are we're actually going to be revealing some secret information. And once in 1,000 times, it'll just be noise. So there is actually a notion of probabilistic non-interference that essentially requires that the distribution of low outputs is independent of high inputs. So we can get there by extending our computational model. I'm going to do some really big hand waving, but let's assume that we have some sort of probabilistic semantics. We're given a configuration, C sigma, we return a distribution over stores. So imagine extending imp with your favorite probabilistic operators. This thing that we're producing here, it might actually need to be a subdistribution. That is, the probabilities of the events might sum to something less than 1. Why might that be the case? Yeah.
There could be some executions that do not terminate.
Right, we might lose some probability mass due to non-termination. So this is part of the challenges of figuring out the semantics of probabilistic execution that, from my looking at Steve H's notes, is, he touched on. So right, the key idea of probabilistic non-interference is essentially that if we have two low equivalent initial stores or inputs, and they execute and produce some distributions, D1 and D2, those distributions should be low equivalent. And by that I mean if we take those distributions over stores and project them to distributions over the low observable parts of the stores, those distributions should be identical. That is, the distributions over the possible observations is not revealing any secret information. Concurrency is another way that we might extend the computational model. And when we extend the computational model in that way, we might have additional ways that information can flow. So we already talked about the idea that race conditions might be a source of non-determinism. We've also touched on how the scheduler might end up revealing information if the scheduler is making choices depending on secret information. You can actually get into more detail and think about the memory models that various architectures use. Sequential consistency being how we tend to like to think at a high level about concurrent code. That is, we like to pretend that a read and a write to a variable happen in some sequential order. But the reality is that there are more complex notions of how reads and writes propagate between cores, and thus what different threads of execution might observe. And so those finer-grained notions of the actual system that's executing might lead to different information flows that we might want to account for in our model. Speculative execution is actually a real source of information leaks. That is essentially a form of concurrency where a computation is speculatively going ahead but might be accepted or rejected. But it's a computation that's going on at the same time that is affecting the state of the machine that might be observable to an adversary. Now, these attacks, Spectre and Meltdown and the like, do actually leak, are actually practical leaks where, for example, encryption keys can be revealed by, through these speculative attacks. Interestingly, we don't actually need a new definition of non-interference. This idea that, you know, the low observable thing should only depend on low observable inputs is kind of the same. It's just that our computational model might need to account for a more realistic notion of how the machine executes and how information might flow between various entities. Okay, I've got 10 minutes left, and I'd like to touch on the idea of reclassification. Now, this is the idea that in practice, non-interference is really just too restrictive. We actually have a lot of real systems where we don't want information to stay at the same label throughout execution. We might have some systems that need to declassify information. That is, to take the confidentiality restrictions on information and weaken them. So, for example, your credit card number is confidential. You don't want to reveal those 16 digits arbitrarily, but your receipt might have the last 4 digits printed on it. So it's somehow okay for us to treat those last 4 digits of your credit card number a little more permissively. who is allowed to see a patient's medical records? Well, when a physician is added to a patient's case, maybe they should be given access to those records. And when they get removed from the case, they might need to be taken away. So that is the confidentiality of the patient's records might be changing over time, being made more permissive. One of my favorite examples is a sealed bid auction. People familiar with sealed bid auctions? Basic idea is that bids are confidential during the bidding process, but they have to be, or at least some of them have to be revealed at the end so everyone has confidence that the auction process was fair. Sorry, was there a question? Yeah.
I'm just wondering, does this only matter for when we're permanently reclassifying, or does things like pseudo fall under reclassification?
Is this only for permanent reclassifications? No, not necessarily. We might be temporarily reclassifying something. And in fact, this notion of declassifying, making confidentiality requirements weaker, is the dual notion of erasure, where we want to make confidentiality restrictions, confidentiality more restrictive. And so you might imagine that the same piece of data might be both declassified and erased, possibly several times during a single program execution. So erasing information might be going back to the credit card, the merchant, after the transaction has been processed, that credit card number might go from being information that they're allowed to use to being so confidential that they shouldn't even have it on their system anymore. And as a result, they actually want to remove it from their system. That's actually a good thing, being able to take that data away from the system and reduce the vulnerability of that credit card number being leaked. A great example is actually with military submarines. When a submarine is underwater, it's a more secure environment than when it's on the surface. And there are actually protocols that various sensitive information, before surfacing, that information has to be encrypted, or for physical things like maps might need to be locked away into secure physical storage before the submarine surfaces. So that's confidentiality is made more restrictive under certain conditions. So when we think about how to handle information appropriately in the presence of declassification, what it means is that we don't just want to say, well, this system declassifies information, so all guarantees are off. A low user can observe all secret information. That would be bad. We actually want to have something that's more expressive, that talks about how we might control the declassification of information. Sapelfeld and Sands introduced an idea of dimensions of declassification, where we can think about the things, the information that we want to declassify. What information are we declassifying? Say the last 4 digits of the credit card number. Who is declassifying the information and who benefits from the declassification? Where in the system or in the label relation are we declassifying that information? And when or under what conditions is the declassification happening? Let's say only after the end of the sealed bid auction can that information be declassified. To give you a concrete example of a version of non-interference that accounts for declassification, a nice simple one is known as the limited release. And the intuition here is that it's specifying what information about the initial low inputs are allowed to be declassified by having a set of escape hatch expressions. So that is, given a program C and a set of escape hatch expressions, A1 through AN, the idea is that if we have low equivalent inputs, sigma 1 and sigma 2, 2 executions, and sigma 1 and sigma 2 agree on the escape hatch expressions, which might include high variables, then the outputs have to be low equivalent. So the idea here is that the only information about secret variables, secret inputs that can be revealed are the results of these escape hatch expressions. So that is, if we have 2 executions that are low equivalent and they agree on the information that's going to be declassified, well, then those low observable executions look the same. There's no additional information beyond those escape hatch expressions that is revealed. Any questions about this? Yeah.
It seems that here we could have exactly the same definition as non-interference by just putting the label low on the A1, the AI.
Yes, this definition does look very similar to non-interference if those expressions A1 through AN were labeled low. But within our model, though, we actually had variables labeled high and low, not arithmetic expressions. So what this is allowing us to do is to say something like, you know what, the average salary of Alice, Bob, and Chuck can be declassified. So that is, one of the escape hatch expressions might be salary of Alice plus salary of Bob plus salary of Chuck, all divided by 3. And that's actually saying something about secret inputs, the salary information of employees. Right? We're not somehow, so this is actually talking about the idea that secret information might be declassified, as opposed to changing the game and saying, you know what, the salary information was public information to begin with. So you know, this in some ways comes down to a modeling question. How do we make sure that our definition of security is actually something that accurately reflects the system we care about? And the more our model does make stretches to encode things, the bigger the gap is between our model and reality, the bigger our assumptions are, the less assurance that we have the reasoning about the model actually translates to guarantees about our real system. Let me just, I did want to give you very, very quickly some info about quantitative information flow. Sorry, messed up my animation there, I'm sorry. Quantitative information flow is really an additional dimension about how much information is revealed. That is, there are some leaks that are undesirable but unavoidable, such as side channels. So we can actually think about side channels, observing how long an execution takes. We could think about what information is revealed, but we might also want to think about how much information is revealed. And by that, what we're going to do is use information theory to measure the leakage of a system. The basic idea is that the amount of information leaked by the execution of a system is the initial uncertainty minus the remaining uncertainty after the end of the execution. So to see this graphically, we have a system that's computing on secret and public information. We have an adversary that is, let's say, initially before the execution of the system. The adversary doesn't get to observe the secret inputs. But the adversary, based on the inputs they're providing, might have some prior beliefs about, let's say, the distribution of the secret. The system executes. The adversary observes the low outputs. And as a result, they might update their beliefs. They might have some posterior beliefs about the distribution of secrets as a result of their observations. So now, given these two distributions, we can actually think about how these distributions differ. And the difference in those distributions is essentially the leakage, the amount of information the adversary has gained as a result of the execution. There's a number of different ways that we can measure that leakage: Shannon entropy, Bayes vulnerability, and so on. These essentially correspond to different threat models. Shannon entropy is kind of just measuring the information theoretic bits of the secrets and measuring how many bits of information are revealed. Bayes vulnerability is kind of a threat model where you're wanting to think about what's the probability that if the attacker had one guess at the secret, say trying to enter a password, that they'll get it correct. Right? And so what's the difference in the probability they'll get it correct before observing the execution and after the execution? Min entropy is related. We might also realize that not all bits are the same value. So we might want to say bits about the encryption key is worth a whole lot more than bits about my social security number, which is secret, but to be honest, it's out there. To give you some information about Shannon entropy, just very quickly in 30 seconds. For Shannon entropy, we can define what's h of x. So where x is a random variable, h of x is the Shannon entropy of x. You can think about that as the number of bits you need to optimally encode the value of x, so that more likely outcomes require fewer bits, less likely outcomes are going to require longer bits. How many bits on average do you need to encode the result? You can also think about it as how much surprise is there in knowing the value of the variable x. So we can define it explicitly. H of x is for every outcome lower x, it's the probability of x times the log of the probability of x. We use log base 2 so that we're measuring in bits. Conditional entropy is similar. The basic idea is conditional entropy of x given y is the information in x given knowledge of y. So if you know what the outcome of y is, how much entropy is there remaining in x. So then we can actually define the leakage in terms of this. The entropy of the secret that is the prior information before we see the execution, minus the conditional entropy of the secret after the attacker has observed the execution, the public inputs and public outputs. So quantitative information flow is actually a very useful way to, for example, think about side channels and try and bound in real systems how much information might be revealed by observing the length of execution. Some references for those who want to dig more into this. Thank you very much. Tomorrow we'll be looking at enforcement mechanisms for non-interference. Thanks. Enjoy lunch.